Hello everyone, this is Saray Kai and I'm presenting for the final project of wireless communication class. My project focus is on evaluation of OFDM system in channel fitting. And let's talk about a little bit on the channel impairments and the signal propagation. All the signals that's transmitted from the transmitter to the receiver has to go through the media, which is the channel, and is full of losses, interference, and noises. And could be classified to large scale path loss and small scale path loss. The large scale path loss is due to the transmitter receiver separation distance, the free space or shadowing effect. Could be an advantage because we can place multiple cells and reuse in the frequency. The small scale path losses are more random and unpredictable. It's usually due to the motion of the mobile device itself, the person moving, or a even smaller scale that is caused by the scattering and reflections of the surroundings. On the right hand side, we can see the large scale fitting is very smooth, and the small scale fitting is jumping around and have a bigger variance. Looking further into the small scale fitting that we can see on this graph is illustrated that is caused by diffraction and reflection and scattering. And the signal would delay and overlapping either destructively or constructively due to out of phase, that the signal will arrive in different power levels. And we can see over here another example of sinusoidal waves overlapping together. The small scale fitting could be classified with two different criteria. One is the time dispersion that's usually environment determined, and it could be classified further into the flat fitting associated with a narrow band and only one resolvable multipath component, or the frequency selective fitting that more than one resolvable multipath components are available. And this could be an advantage because we can select the best signal out of re- replicate signals to do the demodulation and overlooking the noises and other stuff. And the other criteria is frequency dispersion that is usually correlated with mobile device velocity or relative velocity to the transmitter or surrounding elements. The fast fading is a fast velocity of the receiver that causes a larger Doppler shift. The channel variance is faster than the signal variance, and vice versa, the slow fading is a slower speed, small Doppler spread, and lower channel variance. The statistical model for those kind of fittings are Rayleigh or Raycon fittings. Rayleigh fitting is the convolution of two Gaussian distributions, that's complex Gaussian or chi-square, and this is usually characterized by this graph probability density function over here. And we can see that the mean and the variance is directly correlated to the original variance of the Gaussian distribution. And the Raycon fitting is the combination of a Rayleigh fitting with the direct line of sight, which have an amplitude of 1 in this graph that is central located over here. And we're going to look further into Rayleigh fitting in this application because line of sight is rarely available. The Rayleigh fitting we have simulated in the math lab, and the time delay versus the amplitude is showing here to compare different velocity profiles of the Rayleigh fitting. As we can see, the higher the velocity, the bigger the shift, and the frequency changes bigger, and that's a bigger spread, and versus the smaller velocity has a smaller spread. The candidate is OFDM systems. It is the one of the most applied for the LTE and 4G network, and it will be playing a bigger role in the future data transmission. So we're going to look at that further. The OFDM system essentially divides the data into n parallel streams with lower data rates and transmits on subcarrier frequencies. As shown on this graph, those subcarrier frequencies are overlapping to each other, but they are orthogonal to each other by r over 2. They're not correlated, therefore there's no intercarrier interference, and it's better that way. And each subcarrier is modulated with a conventional modulation technique, which is very cheaper and increasing. This will increase in the spectrum efficiency and using more of the bandwidth. And this will prevent the crosstalks between the subcarrier frequencies. And it will be easier to do the demodulation and modulation because each one is a simple conventional modulation that we can do either FFT or discrete Fourier transform. This will also help eliminate the inter-symbol interference and interframe interference because the guard interval or the cyclic pilots are used. The disadvantages are ICI because those carrier frequencies are so close to each other. If any of those frequencies shifted, it will impair the other one that's in the neighboring frequency. This is usually caused by the Doppler spread at a higher velocity mobile devices. The OFDM system block is described here, where the signals are coming in serial and they will change into a parallel sequence that will be mapped into a conventional constellation, BPSK, QPSK, or QAM, and then going through the modulation of inverse Fourier transform or discrete Fourier transform in the case of a digital signal. And the cyclic prefix is added to prevent the overlapping between the symbols and helping with the demodulation integration. And then it goes through this channel that's full of scattering, reflection, that's basically a combination of white Gaussian noise and other fading schemes. And then the serial is changed into a parallel and deleting the cyclic prefix, doing the Fourier demodulation with the FFT and frequency domain equalization, and then constellation demapping, and eventually being changed into a serial signal and restored to its original phase. We have simulated a simple OFDM system with only white Gaussian noises, and we can see here the bit rate error is pretty low with respect to the signal noise level ratio, and this is passed through a QPSK modulation, and we're gonna compare with the next simulation we did. Is inside a Raylan multipass channel, and in this case, the around the same level of signal noise ratio, about 10, we have a 0.8 BER, and versus the other one at 10, we have a very low 10 to the minus 5 level of BER. So we can see that the Raylan definitely adds a lot of bit errors into our system without any methods to eliminating this channel fading. So now we can do is to add an estimator that will do a calculation of least squares or minimum mean square errors from the palette signals that is transmitted for each symbol. And this algorithm is applied with BPSK and 10-tab railing channels. And we can see here that the performance of the MSSC is much better than the least squares because the MSE is directly related to the mean square error that we use as the measurement that we can see. Oh, and now I'm gonna show you the simulation that we have here. So first we're gonna do the railing. That will give us the two graphs that I already showed. And then we do the white Gaussian noise added to the OFDM. This is gonna take a little bit. We can see the bit where arrows versus the serial ones. That's very close to each other. And then we do a final one because we're running out of time. The channel estimator with LS and MSSE. As showing here that I talk about, the MSE has a better performance than LS. And then this is the BPSK modulation with the OFDM system. Added white Gaussian noise and railing fading as well. Okay, it's here. This is the theory and the simulation that's very correlates to each other. Thank you very much for listening to me, and